task general mechanisms of task control kind of emit control signals and regulate our moment-to-moment behavior. So take, input information, go through intermediate processes to output. This is kind of the moment-to-moment processing that we're doing all the time. And I think of task control as kind of riding and helping guide that process and keep us on task. And I think it's fascinating to study because it really is part of everything that we do. And we can see lapses of control in people all the time. But if we think about it, just even in kids, what I think is really fun is making your own sandwich, right? It's a critical step to family harmony. And you have to calculate the right ratio of peanut butter to jelly. You have to remember if your school is nut free. You have to spread to the edge and not tear the bread. And of course, you want to remember when the bus is coming and not forget and just abandon your goal and start to whoa, where'd it go? Butter your face. So an example of a task control failure. So the ways that my lab looks at task control are in the context of mental health and well-being, such that we ask questions like, does task control ability relate to the trajectories of mental health disorders over time? Does task control exacerbate or buffer difficulties across individuals? And are certain developmental disorders more subject to difficulties with task control than others? And could brain information help us understand that? And we also look at task control development in the context of academic skill development, which is more what I will focus on today, which is asking, does the level of task control ability relate to academic skills? Does task control relate to intervention success and how much you could predict growth in an individual over time? And does it maybe relate to learning retention and protecting against learning loss in the face of learning interruptions like summer break or COVID even? So, ways that we have examined task control in the brain are through task control demanding tasks. So we ask children to do something hard relative to something easy. Moments in time when control is needed. So we've been examining consistency of error signaling across different tasks and task initiation signals. And also, more and more the kind of connectivity between putative control related regions of the brain and how that interaction and correlation over time, the functional connectivity of these regions might be important for understanding network communication across the brain as a whole and how control is employed. So today I'm going to focus on the kind of first item during control demanding tasks, as well as the third item, so kind of the connectivity related studies. So I want to show you 4 recent studies from recent alumni of my lab. We're going to talk about the consistency of control engagement across different control demanding tasks in youth, the consistency of cortical hub patterns and resting states, and then kind of switch and spend the second half of the talk talking about variability across individuals, looking at control engagement during reading, as well as the functional connectivity of reading and control related brain networks over time. Okay. So if we start with the first one, consistency of control engagement across control-related tasks. This is work by Dr. Laura Engelhardt in my lab. The question is kind of, do different aspects of task control or executive function engage a kind of core overlapping control network in the brain in middle childhood, or are they kind of task-specific elements of control that show up more? And so, we know from lots and lots of work in task control behaviorally that there are many different skills that we think relate to what we call the kind of overall umbrella of executive function. And there's been a unity diversity model that's been very influential in our work, proposed by Frieda and Miyake, that there's kind of an overall executive function ability. And then that is supported by kind of task independent and unique aspects of executive function. And so today I want to talk to you a little bit about work we've done looking across different putative executive function tasks, such as inhibition, shifting between tasks, and working memory. Was there a question?
No.
Yeah?
No questions so far.
Oh, okay. Okay, I heard something. I'm sorry. All right. Um, okay. So the way that we did this is we converted these type of ideas to pretty classic tests of executive function that have been done in the scanner. So for inhibition or asking kids to keep from doing something that they want to do, we used a classic stop signal task where they're pressing the direction of different arrows, and when a red X comes up, they have to quickly keep from pressing that arrow. And that is staircased and comes faster or slower depending on their ability to stop. And then we had a cued switching task to look at kind of shifting and cognitive flexibility, where they're switching between shape and color, and for individual targets. And then for updating or working memory kind of component of executive function, we used a classic end-back task where children see individual shapes and have to remember the shapes that they saw previously and indicate whether one happened to before that previous shape. Okay, so this is 117 children ages 8 to 14. And here I'm just showing you a main effect picture of the right hemisphere for when children are stopping relative to baseline. And so you can see a set of different regions here, kind of classic stop signal related regions. Here is for the shifting or the cued task switching flexibility task. This is for the cue period when they're seeing the rule and it relative to not performing the target. So they're preparing to engage with the target and apply that rule. And then here's a picture of the end back task for 2 back versus baseline. And if what we're asking is whether or not we see a kind of overlapping set of regions across engagement in these 3 different control demanding tasks. And in fact, that is what we see. We see if you focus on the black regions here in this image, these are regions that were engaged across all 3 tasks and suggest that there's a degree of unity or shared resources when it comes to neural engagement in these 3 different control demanding tasks. And, you know, we were pleased to see this because these regions are very consistent, these black triple overlap regions, with what is known about adult control networks across different meta-analyses. Now, different regions of these networks have been proposed to do different tasks or have different processes within task control. But if we look at them side by side with the triple overlap regions of the children, you can see that the black regions overlap really well. And in fact, are within 10 of the 13 adult regions from our applied literature are highly overlapping. So where they're not is that anterior prefrontal cortex, the kind of very anterior piece over here, and the left inferior parietal. But in general, really consistent overlap, suggesting that the network of control is consistent by middle childhood. But it's different to just say, okay, these overlap in location, but maybe they're just overlapping across the 3 tasks, but they aren't really very strongly activated by all 3 tasks. And so to look at that question, we actually looked at the triple overlap in a slightly different way by looking at the top 15% of voxels and proceeding all the way to the top 1%, the strongest engaged voxels across the 3 different tasks. And so as I play this movie, if you watch the kind of erosion down to the strongest activity, I think you'll agree that the black regions stay very robust across this scaling all the way to the top 1%. So it's not just that they're overlapping across these tasks, they're some of the most robust activations across the 3 tasks as well. So again, we think this is a really interesting way to look at consistency and unity across different control demanding functions, as well as thinking about these 2 task overlap regions or these single task overlap locations and the kind of diversity across different tasks. So, you know, in overall, we see a core set of control regions activated in children, and they overlap substantially in location and priority, similar to adult control networks. But, you know, that gives us an idea that, okay, by middle childhood, control is well engaged in a similar way as adults, but then why is performance still improving over this age? Why are children not as good at control demanding tasks as adults are? And could it be something in the way that these different regions communicate or employ their control signals across moment to moment processing? And so this is really related to thinking about the brain as a series of functional systems that interact and combine to accomplish our goals. And so I'm pivoting here to resting state and how we might get an insight into how these different systems are communicating with each other and integrating information. And so, we have children in the scanner just look at a plus sign and we let them think about whatever they want. But it's been observed in multiple thousands of papers, probably by this point, that there's a really profound correlation across distant regions of the brain that are correlated at this very low frequency bold signal. So here is over 10 minutes of bold, and you're seeing about a 0.84 correlation from the anterior insula on either side of the brain. So a really strong correlation that we think is functional in nature and driven perhaps by the kind of Hebbian functional relatedness, such that regions that work together consistently to accomplish what you do on a day-to-day basis potentially reflects a long history of firing together. So a kind of firing together, synchronizing together kind of idea. And so, if we think about a complex system, though, of like the brain, where there are functional correlations to every part of the brain to each other, some individual nodes of the brain might matter more or less than others. And just to show you what I mean by that, let's take an example of the flight system. So this is Delta Airlines flight paths. And, I think we can easily observe that if you were to knock out certain airports, for example, Austin Airport has been shut down for the last 3 days, pretty much, because we've been in a huge ice storm. And the world has barely noticed. We're not a very important Delta airline node, right? Whereas if Minneapolis was to get knocked out, it would have a much more profound effect on Delta's flight system, despite Austin being a bigger city than Minneapolis, actually. And what's interesting then is there are these hub regions of the brain which might really integrate information and be really critical to how the brain communicates and directs behavior. And if we think about how different individuals might have individual variation in their networks, for example, this is Delta versus United's flight plan. Perhaps everyone has certain nodes, but they may not always be in the same location. So, for example, perhaps there is a Western node that relates to Western travel across the United States. But in United, that's in Denver, whereas in Delta, that's in Salt Lake City. And maybe there's an Eastern node that helps with Atlantic travel, and that is in different locations across the airlines too. But these different airlines have a similar pattern in how they're going to communicate and the way they've organized their systems. And so I want to shift and talk to you about how we're going to look at the consistency of resting state hubs in youth and look for patterns across individuals that show similar organizational strategies. And so the way we look at cortical hubs in youth is through participation coefficient, which is a graph metric looking at each different brain location as a node and the strength of the correlation between nodes as the kind of connection. And we're going to look at participation coefficient, which is how well integrated across different functional networks a particular node is relative to embedded within its own network. So this pink region in the red brain set on the left here is maybe a low participation coefficient because it's only talking to its own functional system, whereas the yellow node, which talks to the blue, green, and red systems, has a very high participation coefficient. And if we look at the right at a whole parcellation in young, healthy adults, you can see that there are different brain locations that are quite critical to connecting different functional systems. And then there are many, many nodes that are just kind of embedded inside their own functional system. And so we decided to look at the idea of cortical hubs and whether they had similar patterns across youths in 500 youth from the ABCD project, so the Adolescent Brain and Cognitive Development Project, funded by NIH. And so we took, that's a public data set, so we took 500 9 to 10-year-olds from there, and then added our own individuals from ages 8 to 17 or so. And each had to have at least 5 minutes of resting state, but the average was 14 minutes or so. And we were also really interested in whether these hubs related to functional outcomes, to cognitive controlled behavior. And the nice thing is that there are kind of similar tasks between the two studies. So I've already shared with you our cued task switching flexibility task between shape and color. And ABCD has a dimensional card sort task that's highly similar with a cue and a target and sorting by shape and color. And so we can compare behavior across those pools of individuals. And then they also have an NBAC like we do, though they have an emotional NBAC. So we're just taking data from when they had the non-emotional stimuli. And you can see that there's good variation across the two groups on these behaviors so that we can see if these hub parcellation patterns relate to actual control related behavior. Okay. So how did we do this? An example of here is that we took the Gordon parcellation, which is a standard functional parcellation for resting state of 333 brain parcels. And we correlated each person's individual matrix across the brain. And then at each individual, we ran community detection for their own functional communities and identified their participation coefficient across those different communities and identified the top 20% of hubs for each person. So that yielded 67 potential functional hubs for each individual. Okay. So then we asked where these hubs are located. So this is different than asking what function or system they seem to be correlating with, but just where are they located. And so here is a map, a heat map of the consistency of hub locations across the 567 youths. And you can see that there's a wide variety, actually. There's some degree of consistency, but not across 100% of individuals. And here, if I just crop to the top 20%, you can see that the major hubs that are most consistent across people are located in control related systems. So the dorsal attention control system, the frontal parietal control system, the cinguloopercular control system, and the default mode network are the primary locations of these most overlapping hubs. But we wanted to not just identify hubs, we wanted to ask, okay, well, across each person's individual hubs, are they showing a pattern that's consistent? Are they Western airport hubs or East Coast airport hubs across individuals that we can identify? And so we took each hub's correlation matrix profile across the major functional systems and then asked, using a Louvain algorithm, whether they clustered across individuals into consistent hub patterns. Okay, and what we found actually were 4 functional hub patterns. The first being what we're terming control default hub profile. And these hubs all had high connectivity between default mode network, ventral attention control, and salience control, and frontal parietal control. And then we found what we're terming a cross-control profile of hubs that had very high correlations in the cinguloopercular, dorsal attention, frontal parietal, salience network. And then what's really interesting is we found 2 separate hubs that we're calling control processing. And so we saw a set of hubs that had a profile that was high with the visual system and the dorsal attention system, the cinguloopercular here. And then we found a separate profile of hubs that was strong with the cinguloopercular, but the auditory and somatomotor hand and somatomotor mouth regions. So we see this kind of different set of maybe regions that interact with the sensory environment around us. And this was particularly interesting because well, I'll get to that in a second. I'm showing you here the average of the 4 profiles across the entire 567 groups, but we determined them actually in 3 separate subgroups. We broke them into groups of 189 to run this so that we could get a measure of whether or not this was a really robust set of profiles. And in fact, across the 3 separate groups, the 4 main clusters, the default control, cross control, and 2 sensory profiles, if you look at the shape as we go across the 3 different subgroups, they're highly, highly similar with each other. And even cluster 5, this kind of baby cluster, also had a very consistent shape across the 3 separate groups. And so we think it's a really robust set of profiles across these young individuals. And we found this really interesting because we found remarkable harmony with work that had been done in the Midnight Scan Club group in adults, where they found 3 set of hub profiles instead of 4. So they found a cross-control set of hubs like we did, a control default set of hubs in pink like we did, but they only found a single control processing set of regions that seemed to go across both visual, auditory, and somatomotor. Whereas in youths, we're seeing that control processing hub set in 2 pieces. And what is also really interesting to note is that in this split of control processing that we see, these are the hub profiles that related to cognitive flexibility behavior. So we see a correlation between the strength of connectivity within these hubs and performance outside of the scanner on the cognitive flexibility tasks. For both of these, though only the auditory somatomotor one survived Bonferroni correction. So these are the only hubs that show a relationship to behavior, and they also are the ones that are most different from the adult profile. And also, we saw a similarity in location of these control processing hubs with visual information with the kind of regions that I saw earlier in my work in age-related differences in cue processing, which is also a flexibility-related task. So we see kind of some overlap in the regions that are showing differences in age and the hub profiles that are differing by age in task control performance. And it's also important to note that across all of these hub profile studies, control is a major player here. So we see that all of the regions that showed various hub profiles involve the control networks to a really strong degree. And so we think that that is really important and suggesting that in this model of task control development, how the task control signals are interacting with maybe the input processes and output processes are ways that developmentally are the most different relative to some of the intermediate transformational processes. So we're excited to explore that further in the future. Okay, so we see similar hub profiles in youth and adults, except in regard to how control networks interact with sensory, motor, and visual processing networks. And we see understanding cortical hub patterns, maybe helping us understand brain function, communication, and vulnerabilities to injury over development. Potentially, this is suggesting a kind of specialized role in routing sensory information to and from the brain's control system. Okay. All right, so that was kind of focusing on the consistency of how we're seeing control and thinking about control across youth and looking at it across different tasks and across different hub profiles of rest. But now I want to kind of pivot and talk about variability of individuals and whether or not variation in ability could have something to play in understanding differences in performance and maybe control processing having a role in that. So we know from work by Miko and others that executive control is really important for reading. And we have to remember, for example, to read direction left to right, self-monitor our comprehension as we're reading, relate what we're reading to the larger world context or to a bigger goal that we have, remembering different exception words that we've read that maybe don't sound out like we thought. But we have a fairly good understanding of how the brain reads, like where the brain reads, I guess I should say. We know that there are some phonological processing pathways and some visual recognition pathways that are successfully employed by strong readers and that are underactivated in struggling readers. But I have a lot of questions still about this type of process, including how control regions might be interacting with the reading system to improve reading over time or to identify struggling readers or identify maybe where the breakdown is happening for struggling readers. And so this is really turning to my work with the Texas Center for Learning Disabilities, which is a large center based in Houston, but also taking place in Austin, where we work with school systems to identify struggling readers across an entire grade, for example, and randomize them to reading interventions designed by the UT College of Education, the Meadows Center here, and Sharon Vaughn. And then my job is to try and scan them before too much intervention gets underway, and then after intervention is over. And this particular study I want to talk to you about was from a few years ago, and it was looking at struggling 3rd to 5th graders, along with grade-matched non-struggling readers. And I'm going to focus just on the pre-intervention scan here, and just ask whether or not we see variation in reading ability that relates to control engagement in the brain. Okay, so we had 108 youth in this particular study, and they've done a large battery of neuropsychological assessments and standardized tests thanks to the various spearheading of different projects inside the Texas Center. And we had them come into the scanner and perform 2 different tasks. We had them do a sentence comprehension task, where they indicated whether sentences made sense or not, as well as the stop signal task of inhibition that I was telling you about before. And we were really curious about whether or not control-related differences in struggling readers that we might see during reading would also show up in a non-reading task. So a kind of question about how generalizable control differences are, because if control is engaging a general network, perhaps differences that we see in struggling readers would show up in non-reading tasks as well. This has been studied before in the context of reading comprehension, and in fact, Myler and colleagues have found differences in the inferior parietal lobe related to reading comprehension ability and during the task of reading comprehension. We were really curious to test a broad number of control-related regions to see if we see differences in the struggling readers during a reading task and during a non-reading task. So during the sentence comprehension, so this is 92 3rd through 5th graders reading sentences. You can see really robust responses, including in very familiar reading related regions. So the superior temporal lobe, the inferior frontal gyrus, the ventral visual word form area. You can see really strong engagement, but also you can see really strong engagement of putative control related regions, such as the frontal parietal network, the kind of lateral frontal cortex, as well as the cingulo-opercular network in the anterior insula and anterior cingulus. And where we saw differences in struggling readers in the control system, we replicated the finding in the inferior parietal lobe, where struggling readers were disengaging this control region more than non-struggling readers, and showed a continuous, actually, relationship with tower scores and engagement in this region, as well as in another control-related region of the cingulo-opercular network, the dorsal anterior cingulate, where this time struggling readers had more engagement relative to non-struggling readers in this region in order to accomplish the same task. So we see some failure to engage some control regions and kind of over-engagement of some control regions in order to perform in the same way as non-struggling readers. And so we thought that was really interesting, but this was in the context of the sentence comprehension task. So we were curious about whether or not this generalized these control-related differences to a non-lexical task, the stop signal task. And so we looked at the stop signal for stopping again versus baseline, stop versus go. So we see really strong engagement of control-related regions in this task. Again, the anterior cingulate, bilateral anterior insula, the frontal parietal networks. But we did not see any significant group difference. So we think that these differences in the employment of control seem to be during reading for struggling readers and not symptomatic of a more generalizable control-related difficulty, though we only looked at inhibition, and it's very possible that different types of control could still be important. Yeah, so we see task-related effects during sentence comprehension, not during an inhibition task. And so these individual differences in the engagement of control seem to really maybe be task-specific, which is really interesting relative to kind of hitting the same regions across different tasks. So they're using them, but they're able to employ them in a way when they're not reading that they aren't when they are. And so this has led us to also continue to be interested in resting state correlations and to look at how these regions might be communicating between control and reading, or between control and math, for example. And so as a final piece today, I'd like to talk a little bit about individual differences in functional connectivity of reading and control networks. And this refers to a project that we're doing in the LDRC, or the TCLD, the Texas Center for Learning Disabilities, right now. And asks not just about how control-related regions might be interacting with reading-related regions, but also how those who come to English reading experience with a very different language background might have different relationships between control and the reading process. So we are looking at, in this version of the Texas Center for Learning Disabilities that just finished, middle school struggling readers, so older students who are harder to intervene on with their reading ability. As they get older, it becomes harder and harder to help them catch up. But middle school struggling readers from non-English speaking backgrounds, which are a growing population, especially in Texas, and they experience often high rates of academic difficulty. So we wanted to ask how the connectivity of task control, reading, and math related brain systems might relate to variation in ability in these English learners, who are quite a heterogeneous population themselves. So again, we have an intervention going on. It was actually a 2-year intervention where we are doing a pre-intervention scan, a 1-year follow-up, and a 2-year follow-up, though the second year was destroyed by COVID. But we are, again, going to just focus on the pre-intervention scan for what I'm talking about today. And we have about 70 English language middle schoolers, English language learners, about 60% of whom are struggling readers. And so their average age is about 12 to 13 or so. And we wanted to do kind of very simple localizers of tasks in the scanner. So we had them do rhyming tests, visual matching tasks, and a simple addition and simple subtraction tasks inside the scanner, as well as asking about different types of control. So instead of inhibition, this time asking about cognitive flexibility. So returning to that cued task switching that I've been talking about today, where they're shifting between rules of sorting by shape or sorting by color. And we are talking about a really high number of differences in how much background in Spanish and background in English these students have and how proficient they are in each language. Um, Here we have a graph of some of the individuals with their percent English spoken throughout the day. So you can see a lot of variability in that, a lot of variability in their self-rated English proficiency and Spanish proficiency. And it's worth noting that, from these schools, over 70% of our sample came from schools with 90% or more students having economic disadvantage. So really economically disadvantaged samples here. The ones in Austin, one set of middle schools were about 40% disadvantaged, and in San Antonio, where we also drew from, greater than 90% were disadvantaged. And in Houston, it was greater than 95%. So the income of our sample was really quite low. And so we were really felt very fortunate to get to work with this set of population. And I don't think it would have been possible without getting into the school system and being able to work inside the schools. To recruit this type of sample on our own would have been very hard to network with and find. And so we're really grateful that many drove up from San Antonio, the hour and a half up a horrible highway, to participate in this study. And so when we had them do the simple reading and math tasks and then just compared regions that were stronger for math than reading in red on the left here, and regions that were stronger for reading than for math in this very simple task, we see the kind of regions that we would expect. But we wanted to then use these regions as localizers, as kind of seed regions for looking at their functional connectivity in the individuals. And what you might notice here, this is graphing each individual's activation within these tasks. That there's a lot of variability within the group average cluster for each individual. So here I'm showing red being 45 individuals, and you can see that very few regions are actually red, that we see quite a lot of variability in the location within the group average blob for each individual person. And I think this is something that we, don't focus on a lot, but that I'm very interested in, is how we as a group see a main effect, but the individual activation varies a lot within these group averages. And so we wanted to kind of recognize that and wondered that if we took a more individualized approach by taking the core activation for each person within these big blobs and looking at the connectivity of those, whether that would improve our signal and kind of account for some of the noise that we get by blurring across individual variations in activation. And so what we did is take our group levels of interest and identify the top voxels for each individual within those kind of group constrained areas. And this is imitating a wonderful paper, Julian et al. Of 2012, of approach of kind of group constrained, individually identified regions. And so then we're going to take each individual's core activity during task and make those the seed locations for correlations during rest. And so we're taking it into a different scan, but using these individualized locations as the seed regions. So we're going to get their correlations across the regions that were most active for each individual for the control task, for the cognitive flexibility task, during math problem solving, and during reading task performance, and get the correlations across those. And we're going to ask whether the strength of connectivity across all of these different types of regions related to reading or math ability outside the scanner, as well as asking just within the correlations in the control regions, just coming from the cognitive flexibility task, whether these yellow regions' strength had anything to do with out of scanner reading and math ability. So when we looked at this, we actually found that the overall connectivity for individualized regions between reading, math, and cognitive flexibility or cognitive control did relate to reading fluency. So it did not relate to reading to math skills, but it did relate to reading fluency from the KTEA task. And the strength of the correlations among the control regions alone just by themselves related to reading comprehension outside of the scanner. So what we think is happening here is the way that individuals are engaging control during task performance as well as at rest has this kind of lingering effect on their ability to perform these cognitively demanding tasks in their secondary language. And possibly, we would see something similar in monolingual students, but we're particularly interested in this sample as well. So we looked at these task-driven regions of interest at rest and found that stronger correlations between all control reading and math regions together related to better reading outcomes, as well as to just the control connectivity themselves relating to reader outcomes. Okay. So I have overall talked about how we see a lot of consistencies over age in the brain's task control system and how it organizes at rest. But we do see some interesting developmental differences in how maybe the communication between sensory systems and control might develop. And then we see that the level of task control engagement during reading comprehension related to standard reading measures. And that the strength of the brain's control network correlations related to reading task performance, using this individualized approach for selecting brain foci from tasks, and that this might be particularly useful in populations with high heterogeneity, like the English language learners in our sample. And overall, I hope that I've kind of convinced you that we see broadly consistent task control patterns and locations, but that these differences might be really interesting and help us understand how individuals vary in different communication across the brain and in their performance. And individual differences in engagement of control may relate to meeting abilities more generally and potentially growth over time. So I didn't talk about some of our intervention work that we also have out looking at control systems inside the reading task and change in intervention response. And basically that by looking at the interplay between these task general systems, control, default mode, for example, with task specific processing like reading and math, may identify a different way to identify individuals who might be struggling, as well as offering new ideas or takes on intervention pathways. Okay. And if you want more study information on the Texas Center for Learning Disabilities, we have a website and a Twitter handle. And I'd like to really thank all of the individuals who do this work. This is definitely a team science, and especially grateful to all of the undergrads who are native Spanish speakers who help us because I do not know Spanish, unfortunately. And of course, highlighting the alumni from the lab whose work I've highlighted here. And of course, thanking the broader Texas Center for Learning Disabilities and all of the funders who make all the work possible. So thank you so much for having me, and I look forward to any questions.
Thank you very much. Does anyone in the room have a question? Go ahead.
While you're taking questions, can I have the last science slide or the takeaway message or the bottom line slide up so I can digest it a little bit more?
Yeah.
While you're taking questions, thank you.
All right, so if anybody online has questions, you can raise your hand. While you're thinking of your questions, I guess maybe I'll start with one. So you open your talk by looking at overlap between these three different executive control tasks and showing there was kind of this robust, I think, DACC area. But that doesn't necessarily answer the question of whether that region is doing the same thing in all the tasks. And then you later, with your reading comprehension and inhibition studies, I think you get the same region showing that associated with reading ability when people are reading, but not in general executive function. So my question is that region doing the same thing across these tasks, or is it working differently somehow when reading is involved versus other cases?
I think that's a really great question. And, you know, it's interesting in the dorsal anterior cingulate because so many different papers have proposed different uses of what that region is doing. I think of it as it's probably doing similar things across tasks, but that it is more or easier or harder to employ in different circumstances. So that struggling readers had to kind of crank that region up in order to do the task relative to non-struggling readers. Whereas another control related region, they had kind of turned down and it should have been turned up. So I think of it maybe more as a dial system than having alternate functions, but I think that that's an open question. And certainly within fMRI at the, 30,000 foot way that we're looking at the brain, we're probably sampling from multiple neuronal populations that could be doing different tasks across different processes that we're kind of merging and don't have the clarity on that at this point. But I think that's a great question. I think, it's one of the most robust regions to see in any task, which suggests to me it has a kind of fundamental purpose, not like a bunch of different purposes, but I suppose that could be an alternate interpretation for sure.
Okay, I think that's a great answer. Thank you. I see Jay Rickle has a question. Jay, you'd be able to unmute yourself.
Really interesting stuff. I'm wondering if you could say a little bit about the implications of your findings for studies of reading that are behavioral rather than brain. So, the kinds of studies that we tend to do where we get a bunch of kids and we have a bunch of tasks. Are there some particular, executive control kinds of tasks that you would, encourage us to throw into our batteries?
Oh, I love that question. We, in our studies, have been having individuals do 8 different executive function tasks, but I understand that that's a little excessive for most people in a time-constrained way. And I believe that has a great paper out now about a kind of common task that she could maybe speak about. But I think thinking about different types of controls and maybe sampling from those a little bit would be nice. We've been focusing on inhibition, working memory, and switching or flexibility. There's a lot of others as well. And I do think getting some kind of measure of executive function can be a really nice addition to understanding the sample.
Thank you.
Any, Tamika?
So I have 2 questions. One is, I'm sorry, if you can give me the quick kind of rundown of your findings for the low SES N of 70 Texas the study in reading and math after you did the individual ROIs. I wasn't sure how that compared to the previous study you were talking about the executive or the ACC and that being not only showing up really for reading tasks, but not for non-reading, and then how that compared to the reading and math localizer based findings that you did in this lower SES sort of population. And then the second question is, if you can, what these findings, based on these findings, and you have the suggestion that adding these kind of things might be helpful for thinking about interventions. And I'm thinking about, there's all these controversies still about executive function, task, embedded or not embedded in reading interventions and so on. So I just wanted to get your thoughts on what you were thinking and what you think, if you had a crystal ball, how would you treat these individuals based on kind of your study and extension of your studies in the future?
Oh my goodness. Okay. The first one was on thinking about the tasks that we have the English language learning students do. Sorry, I'm scrolling through this. Yeah, this is really interesting. I was talking here just about the resting state connectivity results. We are seeing some variation in the flexibility task and reading ability in this sample on the task analysis. The side. And I think it's a fascinating question. Is it the middle school sample? Is it that they're in middle school, that they're English language learners, or is it this aspect of executive function relative to inhibition that's resulting in a variation in achievement related to reading ability? And I can't exactly pinpoint all three of those things vary from the upper elementary sample where we did not see effects in the inhibition task. But I think it's really interesting that cognitive flexibility has shown variation in reading ability in this sample, whereas inhibition did not in a younger sample. And I think that goes to my point that maybe different aspects of executive function might be more or less related to the reading process, but also the age might be a really important factor here in how things go, or, you know, the age at which you are learning English, and things might also then have an impact. So I think it's a really good question. And I think it's really interesting that we do see some differences in cognitive flexibility that we did not see in inhibition in this kind of similar approach. But I think there's much more to understand about that because of the variations across the two samples. And then as far as executive function and interventions, yeah, my understanding is general executive function interventions have not proven to be very effective, that you can train within a particular task really well, but that it doesn't extend across tasks very easily. And so I think it's interesting to think about executive function in the context of reading, because most reading interventions, most reading instruction involves executive function related language, like we need to pay attention to the text. What does this remind you of? How are you thinking about it in the context of what we've read before? And all of these are employing control in how we read. So I think it's a critical aspect. What I think is an open question is whether or not we can dial that up for kids in the context of reading. I would think that in the context of reading is where it would be the more effective than a general control related intervention, given the differences that we've seen in the earlier study. But I think I would love to get your thoughts on how you think executive function and reading intervention go together.
I don't have a strong opinion. I feel like it's too, I don't know. I'm confused about the literature. We don't find too much when we try to do executive function, even embedded type interventions, or we haven't been lucky. If you talk to people like John Gabrielli, I think he would say things like, I think it will impact, it can have a benefit, even executive function, pure executive function training tasks, but probably only for those who are really low SES or kind of have trauma or something that is really kind of putting them at the lower end. And those kids or individuals, you might be able to move more, but maybe not in these normal variation sort of range, including perhaps with more standard reading problems or academic challenges. So it seems like he thought at least you would need to go to the extreme cases to see some real strong evidence with executive function training, or that was his suspicion. But I don't study, or I haven't studied that kind of range of children. And so when we do it, there's nothing, I don't have a strong opinion, partly because I'm confused and my results are not very consistent either necessarily. But
I think it's really interesting. This is a very low SES sample, and we've been looking at executive function abilities inside the larger ABCD profile, and we do see that SES has such a strong relationship to executive function. So it really might be more of a measure of the environment and the kind of access to opportunities as like a really strong predictor of that, or the interrelationship. I guess I don't know which direction, but yeah, I think that's a great point.
Are there any other questions in the room? Anyone else online?
No one has questions.
Okay, go ahead, Frika.
Is it okay, Jessica, if I monopolize and ask another question? Or did you tell me I can't ask for?
Go ahead.
All right. He's the boss here, so, if I may, so then, taking that a step further, so for example, like we've done some lit reviews on prenatal, postnatal, toxicants and these kind of things impacting, and of course, those have a strong relationship with SES and nutrition and all these, a bunch of things that's really hard to dissociate. Prenatal, postnatal kind of impact is really hard to dissociate also, unless you're removing them from that environment, which often doesn't happen. So do you think that these kind of toxicants or other more toxic environments, whether it's environment, whatever you call environmental, do you think that it's easier to have a general impact on cognition, but then, or various executive function that acts differently and it doesn't, I guess my question is it like a different mechanism for those who are really at the low end, because they're exposed to other kind of things and biological or other kinds of toxicants or environment that makes them more prone to these kind of executive function problems? Or is it because they're at the low end, they need every support they can, including those kind of things? And so I guess I'm not sure if my question is clear, and it's not necessarily clear, but if you had kind of further thoughts on that.
Yeah, I'm not quite sure if I can speak to it, but I think I have like competing things. I think the deprivation and difficulty can have a very kind of global effect, right? But also by the time you're in middle school struggling reader, you're pretty frustrated with reading and pretty unmotivated and pretty challenged by it and having a lot of negative experiences with it too. So bringing your attention and control to bear on this really challenging, unpleasant task for you is also, I think, an interesting way that executive function might show up in struggling readers, especially older struggling readers. So, you know, we might have multiple layers at which control is being impacted, as far as opportunity early, opportunity in education, and then motivation and reinforcement of something that is enjoyable and easy for some kids than others, and becomes more of a hardship for kids, especially by the time they hit middle school and the type of samples that we're looking at. So I don't know if that gets at your question, but I think the answers are probably like yes and, right? In the improv speak, where a lot of different layers are impacted by control and can be engaged or rehabilitated in control, but that each individual skill might show slightly different relative impacts of that process. I don't know, those are just some off.
I'd love to hear when you find out more how it relates to whether it's more of these motivational, general sort of focus type of things, or whether there's more to it. I look forward to seeing more of your results. Thank you.
Well, and if anyone has any questions, feel free to email me, and thanks too.
Thank you again for being here and sharing material with us.
Great.
Thank you. Bye.